Hi, this is lecture 6 of ET250. Today what we're going to cover is this concept called the Thevenin and Norton equivalent. And it's very similar to actually equivalent resistors in that equivalent resistors, if you see a bunch of series resistors, you can reduce it to one resistor by adding. You see a bunch of parallel resistors, you can reduce it to one resistor by adding the reciprocal. Well, the question is, well, what if you had a system where it had some voltage sources or current sources? Could you reduce it to a resistor and then a voltage source, or could you reduce it to a current source and a resistor? And so the idea is it takes a complicated circuit and it boils it down to one voltage source and one resistor, which we'll call Thevenin, or you can boil it down to one current source and resistor, and we'll call that a Norton equivalent. All right. What I'll do is I'll motivate it with a reason why would we want to do this. It's kind of similar. Why would you want to reduce multiple resistors down to something simple? It just makes it easier to understand. Um, and easier to analyze. We'll go over the process, like how would you actually do this whole Thevenin and Norton equivalent process, and you'll see the resistor part is actually the same, right? It's this new part, how do I find this voltage? And then same with the Norton process, how do I find this equivalent current, right? You'll have multiple voltage sources, how do I boil it down to one, or one voltage source or one current source. Then we'll look at some examples with reducing a complicated circuit down to a Thevenin-Norton equivalent with where the original circuit has dependent sources, and how do you handle that? Okay, so let's look at a motivating example. So let's say we have two special but simple circuits. So if you look at this one, notice how easy this left side is on both of these, left of these dotted lines. Notice it's just a voltage source and a resistor in series, or a current source and a resistor in parallel. And yes, I have a pretty simple circuit it's attached to, just a resistor. But the nice thing is, imagine if I were to ask you, what's the voltage and current across and through this load resistor in both of these cases, right? And if you are attaching this to a very simple circuit, this is actually trivial, right? So we can easily calculate this IL and VL using the tools we've learned in the last few lectures here. So for example, if we're over here and let's say we know this voltage, we know these two resistors, and I asked you for this current, well, current voltage, well, we could use voltage divider, right? You see two resistors in series in this specific case, and VL equals plus or minus VS times RL over RS plus RL. Yep, that's good. And we use the plus because the voltages, the polarity positives are facing each other. Good. And then once you have that voltage in terms of all these known parameters, you could easily solve for that current using Ohm's law, right? VL equals plus or minus IL, RL positive in this case, and you'd have it IL equals VS divided by RS plus RL. Easy, no problem here, because you've attached the circuit to a very simple case. You go over here, it's the same thing. You have two resistors in parallel in this case. IL, we can use the current divider. IL equals the I source times the opposite resistor times the sum. That's what we have here. And positive because the currents are going in the same direction. Once you have this current, you could again use Ohm's law to solve for this VL, right? And so this, you just plug this guy into the Ohm's law, no problem, right? And so if you had numbers for these three values or these three values, you could punch them into these equations and you would get the numbers. But the point of this story is that I have a very simple, easy voltage and resistor or current resistor, okay? And so this is actually called, the left side here, this is a Thevenin equivalent form where you have a voltage and a resistor in series. Over here on this right side, you have a current and a resistor in parallel. This is the Norton equivalent form. And the idea is we can take a system with like all sorts of elements in it, with resistors and voltage sources and current sources and dependent sources. And we have a process that boils it down to either this one or this one. And that's super nice, right? Okay, so I want you guys to have this main concept. Whenever you hear Thevenin and Norton, I want you to think I'm taking a complicated circuit and I'm reducing it to a simple circuit. Okay, and the two equivalent circuits are either a Thevenin or Norton. All right, and we want it to behave with equivalence. And what does equivalence mean? Same power, IL and VL, under the same conditions. Right? I want the same voltage across and the same current through under the same conditions. That means if I had a complicated circuit and I plugged some resistor into it, I want to see the same power draw as if I plug it into this one or if I plug it into this one. If that makes sense. Okay. So let's look at the process. Okay. So let's say we start with a complicated circuit. And so here's an example of a semi-complicated circuit, and you could have it connected to some other circuit, right? But what we're saying is, let's see how we would reduce this thing to just the Thevenin. So if I can take all this and reduce it down to just a voltage source and a resistor in series, right? That would be really nice, because then you don't have all this like craziness going on. Okay, so here's the process on how to do that. If I want to take this and reduce it to here so that from the perspective of this other circuit, it sees the same thing, i.e. if I had two resistors in series and I had just one resistor, you know, the same idea, except now you just have sources in it. How would you go about it, right? Okay, and just to clarify, under the same conditions, I want this one to behave the same as this one. Okay, the current here, the voltage across here, the voltage across here, I want it to be the same behavior under the same conditions. So if these two are the same circuits, I want the same voltage current interface at both of these. Okay, so let's go ahead and tackle the process. So we're gonna take this example, I'm redrawing it here. Okay, so notice I have 1 kilo ohm, 2 kilo ohms, current supply, 1 voltage supply, 6 ohm resistor. I have my two terminals A and B. Okay, and what I want to do is actually disconnect this from anything. And this is what we'll call the open circuit condition. And to solve for this voltage, I just need to find the voltage here in the open circuit condition, because the open circuit voltage, when I've disconnected it from here, is the Thevenin voltage. And we'll show why later. But that's kind of nice. So what I'll do, I'll disconnect it from anything else. I'll look at these two terminals and analyze this voltage here in the open circuit condition to solve for that value, okay, that equivalent Thevenin voltage. Okay, so let's go and we can now, at this point, it's an ET250 problem, and we can chip away at it, and we can see how do we get this voltage. All right, so some things to note. If this is open circuit, we know there's no current, so we can immediately assume that this current here is 0. Another thing I've done, just as a little trick, you don't have to do this because you can go other ways, but you might want to apply nodal analysis. So that means I'm going to set up a ground here. I can set up a node voltage here and here. I'll call this one V and I'll call this one VT. If this is V, that means by coincidence, the voltage across this current supply is also V, right? With the positive minus. See how these, they're equivalent statements. And I can also start labeling some currents. I'll call this I3 and I6. And notice, because there's no current here, these two are behaving as if they're in series. So the current here through this voltage source is actually the same current here, okay? So the question is, well, in this open circuit condition, what is this voltage, right? What is this voltage across here, okay? Some things we notice aside from just the fact that these two are in series is that these two are also in series, and so we can combine those. This will be 3 kilo ohms here, right? What else can we do? We can do our nodal analysis. So we can do a KCL at this node and do our nodal Ohms laws, and let's just see what we get. So if we look on the left, we have I3 coming in, 2 milliamps coming in, but 6 coming out, right? I6 coming out. So we can write our KCL I3 plus 2 milliamps equals I6. Then we can apply a nodal Ohms law here. And we got to be careful. We can't apply a nodal Ohms law on this side, but because it's a voltage source, but we can apply a nodal Ohms law to this 6 kilo ohm. And so let's write those out. I6 through this resistor is the node voltage, yep, we've called it VT minus 0 over 6 kilo ohm. And the nodal Ohms law over here is I3 equals 0 minus V over the combined series 3 kilo ohms. If you're on a midterm, you would want to write series here. Good. I can plunk these guys in and see what I get. I get minus V over 3 kilo ohms, that's for this one. I get 2 milliamps, and I get VT over 6 kilo ohms here. And I look at them like, okay, not bad. One equation, but two unknowns. But I would like to have one more equation to get two equations, two unknowns to solve this. Another thing to note is I called this node VT because This is the node voltage that corresponds to the same VT voltage or open circuit voltage from here to here, because look at my ground, it's over there. So that's also useful. So I'm really solving for this VT, which is equivalent to VOC. Okay, let's keep going. What is the relationship between this VT and V? If I can find that, I'm done. And if you see it, it's actually a difference of 3 volts. By KVL, 3 volts equals VT minus V. Okay, or I can go loop minus V minus 3 plus VT equals 0. It would be the same thing. So V equals VT minus 3, plug that in. So negative VT minus 3 over 3 plus 2 milliamps plus VT over 6. Multiply everything by 6, both sides of the equation, 6 kiloohms. This cancels, this becomes a 2, and I just crunch, 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 and I get VT is 6 volts. Okay. So if we look at that, we got 6 volts across here in the open circuit condition, right? And then the next thing we want to find is the RT, right? And just to double check, does it make sense that this is a positive 6 volts? Probably. Look, you have a minus to positive here, yeah, and then you also have current going up, kind of making this a higher pressure. Yeah, I think I buy that this is 6 volts from here to here, okay, because I kind of have a stacking of this voltage and this voltage. Okay, that makes sense. So then let's go and find the process, or let me explain the process to find the equivalent resistance, RT, okay? Now, RT is much easier. What you can do, here's the simple process. If you only have independent sources, which we do, not dependent, then you can kill them. And you can kill the sources and solve the equivalent resistance between these two, right? And so how do you kill an independent voltage source, and how do you kill an independent current source? Well, what's the circuit element that makes a voltage source 0? Well, 0 volts. It's a line, it's a short, right? So you can actually replace it with a wire. What's a circuit element that actually makes the current 0? Well, it's an open circuit. So to kill these sources, to solve for the equivalent resistance, we actually short this and open current sources. So we have something like this, right? The 6 kilo ohm is here, short, open, right? And then the 2 and the 1. And now it's just a matter of finding the equivalent resistance between A and B, right? So we find the equivalent resistance between A and B. Well, it's pretty straightforward. This becomes 3 because they're in series, and then this 3 is in parallel with 6. So then I can go, well, 3 times 6 over 3 plus 6, that's the parallel, and RT is 2 kilo ohms. So what that says is I can replace this entire circuit with a 6 volt source in series with a 2 kilo ohm resistor, and it'll behave exactly the same way. Just like that. That's kind of neat. And it's much easier to use this circuit than to use this circuit if you're doing future iterations of analysis, right? And so we can go back to the motivating example. If I took some load resistor and I plunked in here, or I took some load resistor and I plunked into there, and if I can easily calculate the current and voltage for different values of this RL much easier in this system than I can in this system. And both of these will behave the same. They will share equivalence, because what does equivalent mean? Same conditions, like the same RL attached to both, I'll get the same voltage and current. Not too bad, okay? So let me review. To solve for the Thevenin voltage, take your complicated circuit, disconnect it from everything, open circuit, solve for this voltage. If I want the equivalent resistance, this RT, what I need to do is kill any independent sources. If there's only independent sources, solve for the equivalent, what do you call it, resistance, right? And that is it, no problem. Not too bad. Another thing, just to think about it, is, well, what if you had a complicated circuit but no sources? If you do a Thevenin voltage equivalent, would that result in a Thevenin equivalent where this is a 0 volt source? It sure would, because imagine if there was no sources here. This was your complicated circuit, right? If you solve for the VOC of this guy, right, what would you get? 0 volts, right? No current flowing through the whole thing, so 0 volts. So that means your VOC, which is the same as your V Thevenin, would be 0 volts, and you'd just be left with this. That's overkill, right? You're using a Thevenin process to solve for your Thevenin voltage and resistor. But yeah, it totally still works. Like, it's like using a tractor to mow the lawn, but you should result in the same thing, that this would just be a 0 volt answer, right? And this would mean this is a short, right? So if you think of it that way, this is like figuring out how to find equivalent resistance if you have no sources, or, well, what would a source be if I had multiple sources? Okay, let's keep going. Let's look at how do you find the Norton version, where it's the current supply and the, what do you call it? It's the current supply and the resistor in parallel. So there's two ways. If you solve for the VT and RT via Thevenin, so you've got this already, it's pretty nice. The RN and RT are actually the same, and the IN, the Norton current, is actually the Ohm's Law version of this. You just take voltage over a resistor, and that's equivalent to the IN. So that's nice. So if you have the Thevenin, this is the easy way to get the Norton. Okay, but the other way, if you want to go ahead and get the Norton directly, right, you can still solve for the RN the same way. You kill the sources, you know, and you find, you know, R equivalent. But the difference is, if I want to solve for the IN using a similar process, instead of the open circuit voltage, which we did here, you're going to disconnect the circuit and literally short the two terminals and find the short circuit current. That's actually equivalent to the Norton current. Okay, all right. So this is a simple little proof to show why, right? Why is it that the open circuit voltage is equal to V Thevenin, right? So if I have, if you have this situation, if you look at it, if there's no current here, then there's no voltage across, or sorry, no voltage, yeah, no voltage across this resistor. By KVL, this VT equals this VOC. Okay, so that's kind of a nice, easy way to see it. In this case here, if you had a short circuit condition, right, of your equivalent simple Norton, then you could see that by current divider, all the current from here is going to run into here. It's not even going to go into this RN, and so the short circuit current is equal to the Norton current, the source current, right? So by current divider. Okay, this is a very simple way to kind of see that. Hopefully that makes sense, right? And we kind of talked about why is it that RT and RN equal R equivalent when the independent sources are killed, right? So you can imagine if this is replaced with a wire, sure, yeah, this RT is the resistance between these two terminals. If we kill this one and make an open, sure, RN is the resistance you would see between those two terminals, because this is an open and this is a short, right? When you kill it and solve for the RT, right? Okay, all right. So let's keep going, moving here. And this, you know, this just shows that, you know, this behaves via like an Ohm's law, right? And so that's where you get your Ohm's law relationship between VOC, Norton current, and RN, right? Just here, this VOC is the same as this voltage by KVL, and that's the same as this voltage here. All this current's running here. Ohm's law solidifies and brings everything together, and that's shown here, okay? Okay, so now what do you do if you want to do Thevenin and Norton with dependent sources? Okay, well, remember for the Thevenin, you just want to say VT equals VOC, Norton IN equals ISC, right? That doesn't change. The only difference is I cannot directly solve for the R equivalent by just killing the sources. What I would have to do is I would have to solve for VT, VOC first, IN, ISC first, and then do the Ohm's law to solve for the R equivalent, okay? So then I just apply the Ohm's law at the end, all right? So that's the only difference if you have dependent sources. Otherwise, if you have independent sources, then you can do the whole kill the independent sources and then get the R equivalent, okay? Okay, let's go and do an example. All right, so we have an example here with a dependent source, but I still want to take this whole thing and reduce it down to my simple Thevenin equivalent. So let's see what we have going on in this circuit. I have a resistor here of 3 and 6 ohms, and then I have a current controlled voltage source. Do you see the dependency on the current? So it's current controlled. And do you see how the output is a plus minus, not an arrow? So that's a voltage source. So it's a current controlled voltage source. I always have to look for the dependency somewhere. And so in this case, the dependency I notice is here. Good. I see 12 volts across here. Good. And so the question is, find the Thevenin Norton, basically finding the V, the I, and the R, right? And I have to be honest, yeah, there's 4 things, right? Let's look at this. RN, RT, ISC, VOC. There is 4 things. But really, if you find 2 of the 4, you get everything for free, right? If you find RN, that's the same as RT. So you just need to find one of those. RT is RN, the same thing. If you find VT and R, then you can divide by Ohm's law to get this I. If you find I and R, you can do an Ohm's law to get V. So you really only need 2 of the 4 to get your Thevenin and Norton equivalent. Okay, so we have dependent sources. We are going to have to go down the route of finding VOC and ISC first and the Ohm's law last to get this. But let's do the VOC first. The open circuit condition. All right, we know VOC is VT. And if we look closely, since it's open circuit, there's no current flowing through here. If there's no current flowing through here, there's no voltage across this, which means the node voltage here relative to the ground is actually the same as the node voltage there relative to the ground. So actually, this voltage on the outside has the voltage VT because there's no voltage drop across this guy. The other thing to note is if I were current flowing through this current controlled voltage source, it has no choice but to go to the left because this is an open circuit. So actually these 3 elements are all in series. Huh, that's nice. So that will help us peel apart this onion layer and solve for this voltage. Okay, so from the current controlled, current controlled voltage source, I actually have the equation VT equals 2IA. Yes, no problem with that, okay? What else? I can write a nodal Ohm's law on this resistor. IA equals VT, the node voltage, minus 12. And I got to double check. Do I have any element here? I don't. So this node voltage is in fact 12 because this voltage goes from 12 to 0. Good. It's shorted to ground. Good. So VT minus 12 over 6 is IA. Perfect. Let's see, I can take this and just plunk it right in. What do I get? I get a 1 equation, 1 unknown, which is VT. Not too bad. So I can bring the 6 over, so 6, and then I get this, 6 VT, 2 VT, 24, right? 2 times negative 12, negative 24. Bring this over, I get 4, I get negative 24, and VT is minus 6 volts. So what this is saying is my open circuit voltage, which will be my Thevenin, is negative 6 right here across from here to here. Okay, so there's actually a higher pressure down here than there is over there, interestingly enough. Okay. Okay. What else? What else? Let's see. Is there anything else? Yep, I think that's good. So if I keep moving on, I have ISC here, and what I have to make sure to do is get this in the situation that'll help me solve for the short circuit, right? So I got to literally draw a wire from here to here. Now it is tempting. This is a mistake by a lot of students. They will take the numbers from their open circuit condition case and apply it to here. Don't do that. And you can immediately see why that would be a problem. The voltage from here to here in this case is negative 6, but the voltage over here is 0. This is a short. There is no way that that's the same. You can't share those numbers. They'll maybe take the IA from here and use this IA. No, not necessarily true. They might by coincidence in some cases, but you just can't take, you got to almost have amnesia and ignore this and just reanalyze it, okay? So now let's just pretend we're on a blank slate and we want to solve for this ISC. So what we can do is we go, all right, so what do we have here? We have a current, we have the same thing, this voltage, and it looks like what I do is I assume that the node voltage here, this node voltage is actually whatever this is. And I think a better way to do this would be to say, well, let's call this V prime. We'll call this V prime plus or minus, right? You see how this is the same, and I can put a little ground here. Notice V prime, I'm calling this V prime here, but I called it VT on here. This is no longer VT. There's no concept of VT on this side. So I have V prime over here, which is equivalent to V prime over here. And by the current controlled voltage source, I have V prime equals 2IA. And so this guy here is V prime, right? IA equals V prime minus 12 over 6, okay? All right, and I have 1 equation, 1 unknown when I substitute the current controlled voltage source equation into this. And I can solve for IA. So if I bring the 6 over here, I can see IA times 6 equals 2IA minus 12. Bring this over, so I'd have 4IA equals negative 12. So IA is actually negative 3 amps. All right, that's great. I know what this is. This is negative 3 amps. I can do the same nodal ohms on this side. ISC equals V prime. So again, this is V prime minus 0 divided by 3. Okay. And I now know what IA is. I can plug that in here, and I get 2 times negative 3 divided by 3. So I should get negative 2 amps for IN. Okay, the last thing I got to do is do this Ohm's law, right? This little Ohm's law here. I'll put that in here. And negative 6, which is this answer, divided by negative 2, and I get positive 3 ohms. That's good. Remember, we had an issue. If you calculate a negative resistance, maybe some numbers got wrong. So I have a positive 3 ohms, which means that this complicated circuit with the dependent source, 2 resistors, and a voltage supply will behave equivalently to either a negative 6 volt voltage supply in series with a 3 ohm resistor, or a negative 2 amp current supply in parallel with the 3 ohm. 1, 2, and 3, these 3 circuits will all behave the same way under the same conditions. Okay, kind of cool. All right, let's do another example. Okay, so I have no dependent sources. Okay, so this is purely independent, and they're asked to find the Thevenin and Norton equivalent. So in this case, we could either go the open circuit voltage route or the short circuit voltage route. And let's see what, right now we just happen to be in the open circuit condition. So let's chip away at it. We have the open circuit voltage, good. So this is VOC, which is VT. Again, we had that similar trick, no current here, which means no voltage across here, which means by KVL, this node here, this node voltage from here to that ground is the same voltage as the VOC. So actually that node voltage is VOC. That's a nice little trick. What else? The current going through this branch is 3 amps, no currents there. Any other resistance equivalents? No, okay. So let's kind of crunch this through. And so we wrote this down, no current through the right 3 ohm, node voltage equals VOC, and I should say by KVL, right? Okay. I could do a KCL, I1 equals I2 plus the 3 amps, and I could do a nodal analysis, nodal Ohm's law here, nodal Ohm's law here. So I1 equals 12 minus VOC over 3, I2 equals VOC minus 0 over 6. Do you have to use nodal Ohm's law? Do you have to use what do you call it? The nodal analysis? No, you could totally do KVLs and Ohm's laws and all that stuff. This is just one way of the many, right? Okay, so it looks like I can now take I1 and I2, put it in here. And then I have this situation, crunch, 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 one equation, one unknown, and VOC ends up being 2 volts. Okay, so there's 2 volts across here in this situation, right? And that's going to be equivalent to the Thevenin voltage. All right, good. Again, does 2 volts make sense? Positive? Well, we'll see. We have a high pressure over here. We have current flowing this way and kind of going into these ones. Okay, it may be not as easy to see, but yeah, okay, I could see that this might be a higher pressure over here than over here, right? Because that 2 volts would be the same as this voltage over here and this voltage over here. And so, yeah, I could see that higher pressure is going to pushing current down. So yeah, there should be some voltage, 2 volt voltage drop across that. I'd buy that. Okay. So let's keep going. So RT equals RN equals R equivalent. Because I only am dealing with independent source, I can kill them and solve for the equivalent resistance between these 2 terminals. Open circuit, short circuit, current source, voltage source. Okay, so that means this goes. And I think I can see right away, 2 resistors in parallel, 1 resistor in series. And yep, that's right, short, open. Okay, so let me write that down. Open here, short here. 3 and 6 parallel, 3, yep. So 3 in series with this, that's 18 over 9, good. And then so the total equivalent resistance becomes 5 ohms. Not too bad, pretty straightforward to do. Do a little Ohm's law. So let me write the Ohm's law. IN is equal to VT over R equivalent, 2/5. So the IN is just 0.4 amps. So that means that this complicated circuit over here can be replaced with either a voltage source in series, a 2-volt voltage source in series with the 5 ohm, or this thing can be replaced with a 0.4 amp current supply in parallel with a 5 ohm resistor. Okay, that is super nice, right? And so, like I said, if you take another resistor, plug it in, or any other complicated circuit to the same 3, you better get the same voltage and current for the same conditions, right? Equivalent power under the equivalent conditions. That's the whole point of this, right? And again, I want to repeat, this process is very similar to like reducing equivalent resistors. Like if you have a bunch of resistors in parallel or in series, you know how to convert them into something very simple. Well, this is the same idea in terms of you have a bunch of voltage source, current supplies, and resistors mumbled jumbled up. How would you chip away at it and get it to reduce down to this 2 simple little voltage supply and resistor in series, or current supply and resistor in parallel? Neat little trick, and hopefully this whole idea and process makes sense. Okay, don't get lost in the sauce, but just keep that big picture, and hopefully I can help you in class with any misunderstanding. All right, thank you for paying attention, and have a great day.